Hi, welcome to this training video on the Achronix Power Estimator. In this video, I am going to walk you through the various elements of the Power Estimator tool and how to use it. The Achronix Speedster Power Estimator or SPE is a spreadsheet-based tool that enables the user to estimate the total power consumed by the FPGA, which is used for designing the thermal and power requirements of the chip. The SPE uses the vectorless method for estimating power. This means that the power is calculated based on the toggle rate for various resources specified by the user, and this makes it much faster than the vector-based method since it does not require any real-time simulation data. The SPE is typically used in the initial stage of the design process where the architectural details and resource estimates are being outlined to help make crucial design choices. So if a design exceeds the power requirements, it is very helpful in identifying the components that burn more power and revise them. Now let's dive into how to use the tool. The Power Estimator consists of two sections: the main Power Central worksheet, where a summary of all the various power components is presented, and the supporting worksheets, where the dynamic power of the different fabric resources are computed. In the Power Central worksheet, users need to select the appropriate system environment variables that is used for static power computation. The Device Information section is used to select the product family and the appropriate device. The speed grade can be set to any one of these following values. C1 corresponds to the fastest speed grade and the C3 corresponds to the slowest. The characteristics of the device can be set to either typical or maximum. These correspond to typical and worst case device static power respectively as a result of process variations. It is recommended to set the characteristics to maximum in order to account for worst case scenarios. In the thermal analysis section, the user specifies all the device thermal characteristics like the junction temperature and other thermal resistance values to be entered. Both the thermal settings and the device information influence the total static power of the device. Based on the input parameters entered in this sheet and the supporting worksheets, the tool displays a summary of the total power consumed by the device and also a breakdown of the various components like the static and dynamic power, and also the maximum current consumed by all the voltage supplies that are present in the device. Now let's move on to the supporting worksheets. The SPE has separate worksheets for each of the fabric components like the RLB, memories, clock, and also other elements like the PLL, I/O interfaces, and the hard IPs. Each of these sheets take in user inputs like the resource count, toggle rates, and clock frequency at which they operate to compute the total dynamic power. The dynamic power is split into two components, namely the instance and interconnect power. The instance power corresponds to the total dynamic power consumed by the components, and the interconnect power corresponds to the power burned by the routing resources driven by them. Now let's use an example of module that uses about 100K LUTs, 80K flops, and about 10K ALUs. And all of these components operate at a clock frequency of 300 MHz. If the toggle rate is not known, users can leave it at the default rate already specified here, which is 12.5%. The routing complexity reflects a combination of the average fan-out of nets driven by the fabric resources and the routing congestion present in the design, and can be set to any one of these following values. A setting of very low corresponds to a very low average fan-out of 1 to 2 and very low routing congestion, and progresses towards the very high option. If the fan-out and the routing congestion is not known, it is recommended to set to the default value of medium. More details on these options can be found in the Speedster7t Power Estimator user guide. It is crucial to make sure that all these input values entered by the user are as accurate as possible, so the tool can estimate the power that will closely match the expected results measured from the actual silicon. Based on all these input values entered by the user, the power is displayed in the top right corner of the worksheet, and also as a percentage of the total dynamic power present in the device. The worksheet also computes the resource utilization compared to the total device utilization. Similar to the RLB worksheet, the other fabric components like the PRAMs, LRAMs, and MLPs also have their individual worksheets to compute the total dynamic power. The clock network power is calculated in a separate worksheet where the user enters the resources driven by each clock source in the design. Note that each entry here denotes a clock source, and so if a design uses more than one clock source, each of them have to be entered as a separate entry here. For example, let's say a global clock source that is operating at 300 MHz drives about 100K flops, 1000 BRAMs, and 1000 MLPs. The clock network for this clock is displayed here, and the total clock network power for all the clocks is estimated if there are more than one clocks in the design. The power estimator also has another worksheet for the network on chip or NOC present in the device. This worksheet takes in the total NAP count or the network access points that are used in the device, the NAP clock frequency, and the toggle rates as inputs. Based on these inputs specified by the user, the total dynamic power consumed by the NOC network in the device is calculated. Now let's take a look at the hard IP worksheet. Here, the user selects the desired IP and its configuration to compute the dynamic power for each entry. You can also see a list of various voltage rails associated with each of these IPs and the current drawn by each of them. Note that there is a Populate SerDes tab in this sheet. When clicked, this option will auto-populate the SerDes worksheet with relevant input data if the hard IP worksheet has any SerDes-based IPs like the PCIe or Ethernet. Users also have the option to enter any raw SerDes used in the device with the appropriate configuration under the raw SerDes section. Based on these values, the dynamic power consumed by the SerDes lanes is displayed in the top right corner. And also, a select among the various SerDes supplies and also the current drawn with each of these supplies is displayed here. Now, the different dynamic power values from each of the supporting worksheets is summarized in the Power Central worksheet under the Power Usage section for easy readability and analyzing the power distribution across the device. That marks the end of this video tutorial on how to use the Speedster Power Estimator. If you have more questions, please email our Achronix support team at support@achronix.com. You can also download the Speedster7t Power Estimator user guide at the link shown here. Thank you for choosing Achronix.